So now I'm going to explain this article in 2010, which is similar to the ideas of previous lectures because, again, it is written by people like Noah Smith and Andre Martins. So we present a unified view of two state-of-the-art non-projective dependency parsers. So I explained this in one of our lectures, and also I explained relaxed linear program in another lecture. So now this is a unification of these two lectures. This paper is about that. So again, now we see that everything, we can see it as a factor graph, where siblings represent grand features and sibling features. They represent higher order features. For example, these siblings, which has head and two modifiers, represent, for example, one of the head and modifier is here, one of the head and modifier is here. So because one head could have two modifiers, M1 and M3. And so one of them is represented in this label, one of them is represented in this variable node. And you know that factor graph is just a bipartite graph, and we represent the constraints by the factors, not node variables. Node variables are ordinary variables that we set the variables like for example, here our node variables are your edges. You put your edges inside the node variable. So each node is an edge. If it is 1, it means that edge is enabled. If it is 0, or if you are working with label dependency parsing, it represents it has discrete values. For example, it modifiers, different labels in dependency parsing, or universal dependency parsing labels similar to that. And so we are talking about, so the choices about the representation of elements play a major role in algorithm. The elements of Y can be represented as discrete vectors. So Yi take the value in a labeled set. So that is the label of dependency that we use, syntactic dependencies. And for unlabeled case, if we say that it is either it is enabled or disabled, as simple as this. So either it is like 0, 1, 0, 0, 1. This is for unlabeled dependency parsing, or it is like 3, 2, 0, 1, 2, 4, 0. Assume that we have only 4 discrete values that represent 4 different labels. So it represents everything that we have. So edge 1, for example, has label 3, edge 2 has label 2, and so on. Here, this edge is enabled, this edge is not enabled, this one is enabled. And the factor graphs, as you know, is the multiplication of your potentials and your constraints, or C stands for, you can say it is constraints, you can say it is clique. So it depends on the context. In factor graphs, you can think about like that. But constraints are things that are a combination of your variable nodes. So these are variable nodes. So these are factors. You know, it's bipartite. So it could be like this. But the factors are not connected to each other, or these label nodes or these variable nodes are not connected to each other. They're connected indirectly via those factors. So we resolve hard and soft constraints, just like before we used like linear models. Theta is the parameter that we should learn. Phi is the features. Of course, theta is here is shared across factors. And phi is the sum over all those features. So these are hard constraint factors, for example, this one. So the name hard suggests what it means. So I explained dependency parsing of Smith and Eisner in one of the videos. So message passing, we use message passing to identify those marginals that we needed, and after convergence of your message passing, going from variable node to going from root to the leaves and then going back after convergence, we get the belief variables. And we need these belief variables to calculate the probabilities that we need, the probabilities of assignments. And this is the message passing. So this is a 3 hard constraint that you have seen in that video that I explained. And here we are using the variation representation of that. And we have, so a part is a pair, C is a soft, YC is a output assignments. So the same thing, except this idea of variational representation, that because this has a nice representation. I mean, this equation is convex, and its solution is at factor marginals. So that is why it is important to represent and reparameterize like that. So we can think about loopy belief propagation as just a variational approximation. And if you want to understand why it is important, these parameterization, this technique that we use, you need to learn these 3 articles. This one is a nice book, and so it explains whatever you need to know, because I cannot explain all of the parameterization idea in just one slide. So now we have 2 turboparsers. One of them is sum product loopy belief propagation. The other one is LP relaxed one. So sum loopy uses the sum product loopy belief propagation. And all of these things are explained in this book. In this book that I said. And the second one is LP relax map. And finally, we do online learning. So we have the loss, and this is the regularization term. This is the loss of M data points, because we have some training examples for each sentence xi. We have the parse. And this is the aggressive online learning. Because we can compute the gradient, so we can do this gradient descent-like approach. So we are dealing with this family of loss functions. By the way, Connell format for universal dependency parsing is like this. We have ID, we have form, lemma, and here it is the head. For example, says this word is connected to 3. 3 is the number, is the words, the index of the words in that sentence. For example, 1, 2, 3, if we have 7 words, for example, if it is 3, it means that word is connected to this head. And so universal dependency parsing is a really good data set that we can use for dependency parsing. It has for Persian and English and German as well, and many languages. And this is the CONEL-U format. It stands for CONEL-U stands for Conference on Computational Natural Language Learning.